let's get started. Today, we're going to be talking more about areas between curves. And then if we have time, we're going to move on to volumes by slicing, which is going to be a precursor to when we talk about volumes of revolution. Okay, so I think we'll get through areas between curves today. It's not really anything new. Instead of integrating over the x-axis, we're going to integrate over the y-axis instead, but do everything that we did last week. Okay, so a few announcements. You have new homework in Canvas. Homework 1 is due tonight. So if you haven't finished it, you can email me. I have office hours today. You can come see me, all that jazz. Okay, there's a discussion post this week about solids of revolution. So if you look at it right now, you won't really, after today, you might know how to answer the post. And if you've maybe had this class before or have looked ahead, maybe you'll know how. But certainly after tomorrow, you'll be able to answer the discussion post. Okay. Reminder, office hours are Monday, Wednesday, Friday, 10 to 12. And Fridays are via Zoom. And one last announcement I want to make, announcement number 4. Next week, next Monday, everybody's going to be online. Everyone online. Good morning. No, sorry, this is Cal 2.
Yeah, don't worry about it.
So next Monday, everybody's online, okay? I will be out of town on that day. Questions? That also means that Zoom, or sorry, office hours are also online, okay? All right, so to illustrate why we care about integrating over the y-axis, let's look at the example we ended class with last time. So last time we wanted to find the area bounded by these curves, the area bounded on the left by y equals x squared, on the right by y equals 2 minus x, and below by the x-axis. Okay, last time we looked at this and we said, okay, well, I can find the area bounded by all these curves by breaking this up here at x equals 1 and finding this area, which we'll call area 1, and this area, which we'll call area 2. Breaking that up and doing 2 separate integrals and going from there. There's a couple reasons why this is annoying. One, I don't like to do 2 integrals when I can just do 1. Okay, so if instead of thinking of this region as, before we thought of these regions as having a top curve and a bottom curve. This region here has a right curve, this blue curve, which is y equals 2 minus x, and a left curve, which is y equals x squared. Okay, this region, it seems much more natural to think of it in terms of right minus left instead of top minus bottom. Okay, and whenever you always want to take the most natural approach to solving a problem if you're able to. Okay, another reason we might want to think of this problem in terms of the y-axis instead of the x-axis. Well, for this one, it's not going to make a huge difference. But for other problems, it might be the case that finding the area under a curve is very hard to do because the function is not very nice. But if you switch, which is going to essentially be finding the inverse, if you find the inverse function, that function might be nice to integrate. Okay, so this also gives you, what we're about to talk about is going to give you a tool to integrate something that you might not have been able to integrate before, or to find the area of something that you might not have been able to find the area of before. Okay, so I just said that. So the main idea that we're going to use here is we're going to switch from using integration over the x's to integration over the y's to find this area. All right. So this is switching from thinking of this as top minus bottom to right minus left. And anytime you see a region that looks more like it's bounded on the right and on the left instead of the top and the bottom, you'll probably want to switch to integrating in terms of y. Okay. So let's try and do this problem using y's instead of x's. So let me come back here and copy this picture. Copy. Copy. And paste image. There we go. So let's find this area. All right, so before, like I said, before we broke this up this way and looked at region 1, region 2. We're not doing that now. Now, we're going to do this all in one fell swoop and look at this as right minus left. Okay. So the only thing we need to be careful about is these curves now are defined in terms of x's. If I'm integrating over the y-axis, I need x as a function of y. Okay, so I need to rename this curve to be x equals something. So right now this curve is defined as y equals 2 minus x. So how could I write it as x equals something in terms of y? Exactly, just solve for x. Okay, so you subtract 2, divide by -1, you get x is equal to 2 minus y. Okay. Questions on that? Okay, and this curve on the left, again, this is y equals something. Now I want it to be x equals something in terms of y. So how do I do that? Solve for x again. And to do that, what do I do to both sides? Take the square root. Very good. When I introduce a square root, I need to do a plus or minus the square root of y, right? So this is a function of y. I need to pick one. I need to pick either the plus or the minus. So which one am I picking here? Plus. And the way you can see that is, well, if I just pick any old point on this curve, before I would think of this as x and I would find a y. Now I'm thinking of this as here's a y, the x that corresponds to it is positive, right? So I want to take the plus square root. Okay. Okay, and so now we can go through and do the Riemann sum stuff that we did before in terms of y's now instead of terms of x, but you're going to get the exact same thing. You're going to find that the area of a region bounded on the right by f of x and on the left by g of x, that region is just given by the integral of f of now y minus g of y dy. And now we need bounds in terms of y. So what are my bounds going to be here? What does y range between? 0 and 1, exactly right. 0 and 1. And so now looking at this, f of y, that's the function that's on the right. So what's the function of y that is sitting on the right side of this region?
The 2 minus y.
Exactly right. That's the 2 minus y. So this is going to give me the integral from 0 to 1 of 2 minus y. And what's the function of y that sits on the left side of this region? Square root of y. Very good. So 2 minus y minus the square root of y. Well, we should all know by now that I almost never actually write square roots. I'm going to write this as y to the 1/2 dy. Okay. Questions on this so far? Okay, and then from there, this is an algebraic function. I can integrate using the power rule, term by term, right? So what's the integral of just 2 with respect to y? Careful, that's the derivative.
Yeah.
It's y. Careful, we're integrating with respect to y. Yeah. And so, very good. 2y minus, what's the integral of y with respect to y? So you're looking at the y to the 1/2. That's what we're going to be there. But for this one first, I think Mark said it was y squared. You add 1 to that exponent and then divide by the new exponent, right? Very good. And it doesn't matter that these are y's. Again, the d whatever, you can treat it like an x, like you're used to, but we're using y's here, and that's fine. Okay, and then minus, just like Connor said, the new exponent here is going to be 3/2, 1 plus 1/2, or I guess 1/2 plus 1, right? So I'm going to get y to the 3/2 divided by that new exponent of 3/2. I evaluate this at y equals 1 and y equals 0. Everybody okay with that so far? Everybody at home? Any questions? Okay, so let's simplify this a little bit. This is 2y minus y squared over 2. And then if I'm dividing by 3/2, that's the same thing as multiplying by 2/3, right? So minus 2/3 y to the 3/2. And then I plug in y equals 1, y equals 0, and take a difference. Okay, so this is equal to 2 minus 1 squared over 2 minus 2/3 times 1 to the 3/2 minus 0 minus 0 minus 0, right? And this is 2 minus 1/2 minus 2/3. Now, if you were on an exam and you felt like you were running out of time and you left your answer right like that, I would give you full credit, but I would be a little sassy. I would write, you can simplify this more, couldn't you? Okay, but technically this is an exact answer, right? This is an unsimplified version of the exact answer. So just so everyone knows. So this is 2 minus 3/6 minus 4/6. So 2 is 12/6. Minus 3 minus 4 is minus 7. And this is all over 6. So this is 5/6. Okay. Questions on that? All right. So in general, if we want to find the area bounded by two functions of y, we can use the Riemann sum process that we used before. So let's look at just the general region bounded on the left by, this is x equals f, bounded on the right by x equals f of y, and bounded on the left by, this is x equals g of y. Okay, so if we want to find the area between these two curves, sort of that little kind of teardrop shape, well, we do the exact same thing we did for functions of x. I don't know how to find the area of that weird shape, so I'm going to cut it into a billion little pieces and take the area of each of the little rectangles I get and add them all up, okay? So instead of drawing out all of the little pieces, this is what I'm going to do. And this is what we're going to do for the rest of the semester here. We're going to take a little slice, one little slice, okay? And it's here at, we'll say, yi, we'll call this yi star, okay? So there's a little slice centered at yi star. It doesn't have to be centered. Yi star could be any point inside of that rectangle, right? So then the area of this rectangle, which I will color in SU blue, is, well, the area of any rectangle is just its width times its height, right? Its width, well, over here, this edge goes to the right a length of f of yi star, right? Over on the left, same thing, but now it's g of yi star. So its whole width then, well, the length of any line, if you know where the right edge is and you know where the left edge is, the length of that line is just right minus left, right? So its width is f of yi star minus g of yi star. Okay, and then its height, well, I'm just going to assume that all of my rectangles, I'm only looking at one rectangle, but I assume that all of my rectangles have the same width, or sorry, height, in the y case, of delta y, right? Delta y. Come on, shrink. So then the width of this one rectangle is this, f of yi star minus g of yi star times delta y, where the yi star, you can find the y0, the yn, delta y given all of the points that you care about, like the starting point down here at y equals a, and the end point up here at y equals b. If you know how many rectangles you're using, you can find delta y. What would delta y be? If you know you're using n rectangles, then delta y would be what? Exactly, it's just your whole length, b minus a, divided by how many rectangles you're using. Exactly right. So you can find all that stuff just like we did before, but then once you do that, this is for what one rectangle? Well, I want to do this for all the rectangles that I'm looking at. So I take a sum. Okay. The sum gives me the approximate area. If I want the exact area, then I take a limit. As n goes to what? Is it as n goes to 0? Infinity, right? I'm taking the limit as I'm using more and more and more of these rectangles. So I want the limit as n goes to infinity of f of yi star minus g of yi star times delta y. This is the exact area bounded by these curves, of the region bounded by these curves. But then what's another way we can write this limit of this sum?
Put it as an integral.
Exactly right. This is, by definition, the definite integral from a to b of f of y minus g of y. Your book likes to put parentheses here. It really doesn't matter. dy. Okay. So if you want to find the area bounded by, sorry, the area of a region bounded on the left by g of y and on the right by f of y, you take this integral. Questions on that? So that works just like it did in the x case. Again, we're going to see time and time again this process come up. I don't know how to find the volume of something. Okay, well, I'll approximate it with a bunch of slices, find the volume of that slice, and then add up all of those volumes. I don't know how to find the surface area of something. Okay, well, I'll take a little line, I'll find the length of that line, and then add up all of those and take a limit. I don't know how to find the work done by some force. I'll approximate over a small distance and so blah, 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 blah. This is the process that we use over and over and over again in this course. Okay, and in life, it's an incredibly useful thing to do. Okay. Questions? Okay, so let's find the area of the region bounded by the curves y equals 1 over x squared, y equals 2x, and y equals 2. All right. So here I have a picture. I haven't labeled the curves. So what is this curve here? Which one is that?
Y over X.
Very good. This is y equals 1 over x squared. Which curve is this? 2x. Very good. Y equals 2x. And this bottom curve? Yeah, that's pretty clearly y equals, actually, that's not right at all. That should be y equals 0.25. That's my fault. That should be a y equals 1/4. I think I had this problem written differently before. And I forgot to change the y. So make sure to change y equals 2 to y equals 1/4. Okay, so you guys tell me, and gals, how should I do this problem? There's a couple of ways. I'm trying to find the area bounded by those curves, the area of the region bounded by those curves. Should I integrate in terms of x or in terms of y? In terms of y, and why should I do that?
Because it's not really a up and down curve, it's more of a left.
Exactly. This isn't, if I'm when I'm looking at this region, I don't really have one top curve and one bottom curve, right? I have really a right curve and a left curve the whole way up and down. Whereas if I was looking at this in terms of x, well, top minus bottom, top minus bottom, top minus bottom. But then here it changes, right? Top becomes 1 over x squared, and bottom is still y equals 1/4. But it's going to be annoying to have to split up that integral to integrate in terms of x. So why not just do it all at once in terms of y? Okay, so we're looking at right minus left now. Okay, so when I do that, if I'm taking this integral in terms of y, well, my functions are in terms of x. So again, I need to solve these guys for x. So this curve, which is y equals 1 over x squared, what is it in terms of x? X equals
x equals the square root of y.
very close to square root of 1 over y. Yeah, because we'll flip these, right? I'll cross multiply, if you will. So I'll get 1 over y and then take a square root. Yes, very good. And this one, again, I'm taking the positive square root because if I look along the bottom, the x-axis, my x's are all positive. So I need to take the positive square root here. Okay. And another way to rewrite this that's going to be useful when we integrate is y to the minus 1/2, right? Very good. All right, the curve on the left, y equals 2x. Well, what is this in terms of a function of y? Yeah, just to solve for x here, or sorry, yeah, to solve for x, I just take that equation and divide both sides by 2. All right, the only other thing I'm going to need, I know my bottom bound, the only other thing I'm going to need is I need to know what is the top bound here when I integrate, because I'm going to find the integral from, well, I know the bottom is 1/4. I don't know the top yet. Right, which is y to the minus 1/2, minus left, which is y over 2. So what is the top bound there? Perfect, exactly right. To find that, I could find where does y over 2 equal y to the minus 1/2, because that point that we're looking for is just where those curves intersect, right? Those curves intersect where y over 2 equals y to the minus 1/2. So I'll multiply both sides by, well, you guys tell me, how do you want to solve this equation? Solving equations is also part of a calculus class. There's a couple things you could do. Someone throw out some ideas. Factor? Yeah, you could factor. Once you get more and more used to factoring, this isn't that bad, really. So first, to factor, I need to get everything over on one side. So I'll subtract that over like that. And then what would we factor out? Well, I'm going to factor out this thing. So I'm going to factor out a y to the minus 1/2. Well, when I factor y to the minus 1/2 out of y to the first, you can think of it as dividing by y to the minus 1/2 to find what should be left, and that's going to be y to the 3/2. Right? So that's when I factor that out there. Divided by 2 minus, well, y to the minus 1/2 divided by y to the minus 1/2, that's 1. This is equal to 0. How else could we have solved? There's always more than one way to do almost any problem in this class. How else could I have solved this equation here?
Could you have put the right side as 1 square root of y plus 1 square root of y?
Yeah. I could have, that exactly right. You could have written this. You could have written as 1 over square root of y, and then you would multiply both sides by y to the 1/2, and then that cancels, and you're left with this equation. Yep. Very good. All right, but either way, no matter what, I'm going to end up with the fact that y to the 3/2 over 2 minus 1 is equal to 0, because y to the minus 1/2 equals 0 doesn't have any solutions. So that tells me that y to the 3/2 over 2 equals 1. And that tells me y to the 3/2 is equal to 2. And so what do I do to both sides here? Y is equal to, how do I undo y to the 3/2?
No, multiply by 2/3.
I think you're thinking of the right thing, but it's not multiplying by 2/3. I take it to the 2/3 power, right? Yeah, very good. So I take both sides to the 2/3 power, right? Oops. 2/3. So y is equal to 2 to the 2/3. So that's where these curves intersect in terms of y. Okay. So this integral up here is going to be the integral from 1/4 to 2 to the 2/3 of y to the minus 1/2 minus y over 2 dy. So from there, it goes essentially the exact same way that that first problem went. So y to the minus 1/2, what's that integral of y to the minus 1/2? Perfect. I add 1 to the exponent, so minus 1/2 plus 1 gives me positive 1/2, and then I need to divide by the new exponent. Minus, what's the integral of y over 2 with respect to y? Remember, this is y to the first. I'm going to erase to the first because it looks like y prime.
would be y squared divided by 4.
Y squared, oh, careful, if you divide by 4, then you don't really need the divide by 2. But yes, in general, the 1/2, you can think of it as the 1/2 is out here, and then the integral of y is y squared over 2. And so you're going to get y squared over 4 either way. Okay, so I'm going to write it as y squared over 4. Okay, so we've integrated, and now I just need to plug in y equals 2 to the 2/3, and y equals 1/4, and then take a difference. And this is not going to be a nice number. So I'm going to simplify a little bit. Oh, I need to add a page. I'm going to simplify a little bit. This is the same thing as 2y to the 1/2 minus y squared over 4. Evaluate at y equals 2 to the 2/3 and y equals 1/4. All right, so when I plug in y equals 2 to the 2/3, well, I'm going to get 2 times 2 to the 2/3 to the 1/2 minus 2 to the 2/3 squared divided by 4. Very gross, but life is gross sometimes. Okay, then I plug in 1/4. So minus 2 times 1/4 to the 1/2 minus 1/4 squared divided by 4. I'm going to do a little simplification, but not much, because again, this is nasty. Okay, so 2 times 2 to the 2/3 to the 1/2, that 2 from the 2/3 and the 1/2, those cancel, right? And that just becomes 2 to the 1/3. Minus 2 to the 2/3 squared. Well, that's going to be 2 to the 4/3. And I divide that by 4. Okay, then minus the square root of 1/4. That's just 1/2. And so 2 times 1/2, that's just going to give me 1. That one's at least nice. And then lastly, 1/4 squared, that's 1/16. So then I divide that by 4. This is 1/64. And that's just how I'm going to leave it, because that's nasty. If you want to plug that into a calculator, feel free. But that's that. I don't want to spend the whole class simplifying a number. Are there any questions on this example? Okay. So let's look at an example where maybe it's not as obvious what we need to do. Find the area of the region bounded by the curve y equals x to the 4th and y equals x to the 6th. And I have not given you a graph here. So we need to do a little bit of graphing ourselves. All right, so y equals x to the 4th. I should try and make the line straight. Go. All right, so here's x, here's y. So y equals x to the 4th, and y equals x to the 6th, and y equals x to the 8th, and x to the 10th, and x to the 202. Those all have roughly the same shape, right? What shape do all of those, what shape does x to an even power, positive even power have? Yeah, it roughly has a U shape, right? And the higher the exponent is, the more flat the U is closer to the origin. Okay, so y equals x to the 4th is going to look something like, it looks kind of like a parabola, but it's a little flatter at the bottom. and then y equals x to the sixth. Looks very similar. But it's even flatter. So this curve here is y equals x to the sixth. This curve here is y equals x to the fourth. If you didn't know what these look like, you could have always plotted them in Desmos. But I'm trying to find that area right there, right? So how can I find that area? Well, I'm finding the area of a region bounded by a couple of curves, right? So I know it's going to be an integral of something minus something. Maybe it's going to be top curve minus bottom curve. Maybe it's going to be right curve minus left curve. We have to look at this and decide. So what do we think? Is it going to be top minus bottom or right minus left? Which one makes more sense here? I would say top minus bottom here. The whole way we have x to the fourth is on top, right? X to the sixth is beneath x to the fourth in this region we care about. You might say, why didn't I look at this region out here? And why didn't I look at this region out here? Why not? Well, I just, yeah, I just drew and filled in some area, but
It's not.
yeah, exactly. And we don't want the red regions there because those aren't bounded. Those areas, if you try to find that area, it'd just be infinite. Those blow up, go off to infinity. These region, the blue regions that I shaded in there are the only regions that are bounded by these curves. Okay. So we're gonna do top minus bottom. Okay, so that means I need to find the integral from somewhere to somewhere of the top curve, which it looks like the top curve is x to the fourth minus the bottom curve, x to the sixth dx. So the only thing I need now are bounds on this integral. So where are the bounds going to be?
0 to 1.
I got wherever they equal each other, and I got 0 to 1. And I agree with wherever they equal each other. It looks like 0 to 1 would actually just be that, right? It'd actually only be the right. But there's also this left side. And you can actually, if you just find the area from 0 to 1, because of the symmetry, you could just multiply by 2. Or we could find where these curves equal each other. So to find where these curves equal each other, that's where x to the fourth is equal to x to the sixth. Okay, someone tell me how they want to solve this.
Subtract x to the x on both sides.
Yes, very good. So I'm going to subtract. So I have all my x's on one side. You could have subtracted everything to the right if you prefer things on the right. Then what do I do? Good. Factor out x to the fourth, very good. So when I do that, I'm going to be left with a 1 from this term minus x to the sixth divided by x to the fourth gives me x squared from that term. Okay. This is all still equal to 0. So looking at this, I either have x to the fourth is equal to 0, which tells me that x is equal to what? 0, or I have 1 minus x squared is equal to 0. So that x is what? Plus or minus 1. So we do get an x equals 0 solution. The thing to be careful about is, yes, those curves do equal each other there, but the curves don't switch. The curves don't switch which one is on top and which one is on bottom. Okay. So x equals 0 is not really a solution we care about here. I only care about the fact that those two curves equal each other at -1 and +1. Okay. Top minus bottom. Okay. All right, and to be quick, this is x to the 5th over 5 when I integrate x to the 4th, minus x to the 7th over 7 when I integrate x to the 6th. I evaluate at x equals 1 and x equals -1. So that's going to give me 1/5 minus 1/7 minus -1/5 plus 1/7 when you plug in the negatives. So this is going to give me, well, 5 and 7, the least common, greatest common, no, least common multiple is 35, right? So I'm going to get 7 minus 5. So that's going to be, if you work it out, 2 over 35. From that first little bit, and then minus 2 over 35. Does anyone need to see where I got 2 over 35? Common denominator. Okay, and so your final answer is 4 over 35.
Professor Matheson, I have a question.
Yeah.
So why is it like x to the 4th minus x to the 6th and not the other way?
Excellent question. So there's a couple ways we can think about this. First and foremost, when you're doing these problems and we don't have an intuition for the curves, go and plot it. Okay, so here's x to the 4th in red. Here's x to the 6th in blue. Okay, when I was learning, yes, I thought bigger power, that's going to be the one on top. But between x equals -1 and x equals +1, the blue curve at Chase, come on. The blue curve is actually below the red curve here. And the blue curve, if I pull up, the blue curve is x to the 6th. Okay, so that's one reason is if I just plot the curves, the blue curve is below the red curve. Now, you might ask, well, why? Bigger power, shouldn't that one be on top? Well, if you think about x is between plus and -1. So x is smaller than 1 in absolute value. Okay, so think about like 1/2 for a second. If I take 1/2 and I square it, I get 1/4, right? So x to the 1/2 is smaller than just, or sorry, 1/2 squared is smaller than 1/2. Okay, so for numbers smaller than 1 in absolute value, if I start raising them to powers, they get smaller, right? Which is why x to the 6th actually lies below x to the 4th. Larger power actually means smaller number if the absolute value of the number is less than 1. Excellent question. Any other questions? Okay. So good. All right, so we got one more example that we're going to get through, and this comes up on the homework. So in business, you have what's called a marginal cost. So a marginal cost to produce some product is just the derivative of the cost function with respect to the number of products. Okay, now that's what I've said here is actually not true. The marginal cost is the cost to the difference in the cost to produce one more product than what you're currently making. But if you're making a large number of products, then you can approximate that really, really well with the derivative, right? So the marginal cost, let's say if I own a factory that produces dice, and the cost, the total cost to produce X dice is given by this C of X is 0.05x squared plus 20x plus 10, then what would the marginal cost be? Well, the marginal cost is just the derivative of the cost function with respect to the number of products, okay? I'm calling X the number of dice I'm producing. So the marginal cost is the derivative of this. So what do I get for the marginal cost? Well, I need the derivative of 0.05 times X squared. What is that? Good, 0.1x plus the derivative of 20x. What's the derivative of 20x? 20. Wow, Chase. Plus 20 plus the derivative of 10. What's the derivative of 10? 0. Very good. So the marginal cost, that's my cost function, 0.05x squared plus 20x plus 10. Then the marginal cost, which again tells me if I'm making 100 products, the marginal cost tells me how much it's going to cost to make one more, that difference in cost. Okay, so the marginal cost is given by this 0.1x plus 20. The marginal revenue is defined the same way. If I'm making so many products and I know my revenue function, then the marginal revenue will tell me how much money I can expect to make if I make one more product. It'll tell me the difference of how much more I expect to make. Okay, so the marginal revenue is just the derivative of the revenue function. Okay, profits, which is what all businesses want to maximize, the profit function is revenue minus cost. Is how much money you take in minus how much money you spent to make that money, right? So then businesses want to optimize that. We're not going to optimize anything today. We're just going to look at, if I know the marginal cost, then how could I say what's going on with my business? Okay, so a factory is selling cell phones, and the marginal cost function that they found was C of X is 0.01x squared minus 3x plus 229. Okay, where X is the number of cell phones produced. They find that they have a marginal revenue function of 429 minus 2x. Okay. Find the area between the graphs of these curves and X equals 0. And then we want to say, what does that area represent? Okay, so marginal cost. Marginal cost plus 229. So here's plus 229. Looks something like this. The parabola. There we go. Does something like that. This is a very rough sketch. If you want to see a more exact graph, well, from Calc 1, we have the tools to make that, but I just want to see really, if I'm finding the area bounded by a region, the area of the region bounded by curves, I just want to know what function is on top, what function is on bottom, right? All right, so the marginal cost starts there at 229 on the y-axis. Marginal revenue looks like this. It starts up here at 429 and then goes down like that, right? So again, this was a very rough sketch, but it gets the idea across of what function is on top and what function is on bottom, right? So what curve are we looking at? That's the top curve for us. R of X is the top curve. So we want to find the integral of R of X, little r minus little c dx. And we know we're starting with X equals 0, and we want to go until our top bound, which, how would I find that top bound? Which is right here where they intersect, right? How do I find that top bound?
Simply.
I set those curves equal to each other, right? Those functions equal to each other. So we're gonna pick up here tomorrow. I will solve that equation that we get, and then we'll pick up from here tomorrow. Okay. So this problem like this comes up on the homework. So if anyone has any questions, let me know. All right. Thank you all for being here. I have office hours today from 10 to 12. If you have any questions, come see me, and I'll see everybody tomorrow.
Thank you.